this video, we'll cover the topic of the graph, domain, and range of a logarithmic function. Logarithmic functions are the inverses of exponential functions. The inverse of the exponential function y equals a to the power of x is x equals a to the power of y. The logarithmic function y equals log base a of x is defined to be equivalent to the exponential equation x equals a to the power of y. Y equals log base a of x only under the following conditions. X equals a to the power of y, a is greater than 0, and a does not equal 1. In this topic, we are going to be asked to find the domain and range of a logarithmic function. The domain of a function is the set of possible values of the independent, or x, variable of a function. The range of a function is the set of possible values of the dependent, or y, variable of a function.
Those definitions sound familiar. Can we look at an example problem to see how we'll apply them?
Of course! Say we are asked to graph the function g of x equals log base 2 of x minus 2 and give its domain and range using interval notation. Looking at the minus 2 within the parentheses here, we can tell that the graph of g of x equals log base 2 of x minus 2 is a transformation of the graph f of x equals log base 2 of x. In our previous lecture, we went over different types of transformations for logarithmic functions. Here are a list of possible transformations you might see in your example problems. This is not a complete list as other transformations are possible. These are just the possible transformations that you might need when working on these problem sets. So let's first look at the graph of the function of f of x. We can graph the function of f of x by plotting 5 points that it passes through. So for this graph, we can plot the points 4, 2, 1, 0, 2, 1, 1 half, negative 1, and 1/4, negative 2.
How do we know that?
We can find this out by plugging in 4, 1, 2, 1 half, and 1/4 for x in the function of f of x and getting the outputs of 2, 0, 1, negative 1, and negative 2. This tells us that the graph of f of x passes through the points of 4, 2, 1, 0, 2, 1, 1 half, negative 1, and 1/4, negative 2. For more practice finding the values of and graphing logarithmic functions, you can review the topic Graphing a Logarithmic Function, Basic. Does the graph of f of x have any vertical asymptotes?
I'm not sure. How can we tell?
The function f of x does have a vertical asymptote at x equals 0. We can find this out by first replacing f of x with y. By definition, y equals log base 2 of x means the same thing as 2 to the power of y equals x. By testing some numbers for y, we can see that 2 to the power of y is always positive but gets very, very close to 0. In other words, x is always positive and gets arbitrarily close to 0. This means that there is a vertical asymptote at x equals 0.
Now that we have our graph of the function of f of x, we just have to find the domain and range to complete the problem, right?
Almost. Remember that the graph of f of x is just the graph that we are starting with. The graph of g of x that we will submit as our final answer will be a transformation of the one we see here. The same goes for the domain and range. We will find the domain and range for f of x, but we must apply the transformation before we can submit our final answer. Let's start with the domain. For the domain and range of the function of f of x, we will have to take the vertical asymptote into consideration. Remember, the domain is the set of possible x values for the function of f of x. Since we have a vertical asymptote at x equals 0, we know that the domain of the function of f of x will start at, but not include 0.
So to write it in interval notation, we write it with the parentheses as opposed to a bracket, right?
Very good. The parenthesis tells us that the 0 is not included. The function only approaches it, never reaches it. If it reached it, we would use a bracket instead. To find the other end of our domain, we will again consider 2 to the power of y equals x. Just like the value of x can get extremely close to 0, it can also get extremely large, meaning that the domain of the function of f of x carries on all the way out to infinity. Do we use a bracket or a parenthesis to represent this part of the domain?
Well, since we can never actually reach infinity, it can't be included, so we write this with the parentheses, right?
Yes, so the domain for the function of f of x is 0 to positive infinity. Now we must find the range. As we can see represented on the graph of f of x, there are no restrictions on the y value. Therefore, the range is negative infinity to positive infinity.
Now that we know the graph for the function of f of x equals log base 2 of x, are we going to transform it to find out what the graph for g of x equals log base 2 of x minus 2 will look like?
Absolutely. Remember, when something is added or subtracted to the x inside of the parentheses, it results in a horizontal shift of the graph of the function. In our case, 2 is subtracted from x, meaning the entire graph will shift 2 units to the right. To plot the graph of the function of g of x, we can find out 5 points that will be on the graph by shifting the points from the graph of f of x. So 1, 0 becomes 3, 0, 2, 1 becomes 4, 1, 4, 2 becomes 6, 2, 1 half, negative 1 becomes 5 halves, negative 1, and 1/4, negative 2 becomes 9/4, negative 2, after we shift them 2 units to the right. This can be done by adding 2 to the x values of the points we found for the graph of f of x. We now have our graph for the equation g of x equals log base 2 of x minus 2.
What happens to our vertical asymptote now that we've transformed the graph?
We can see on the graph of g of x that the vertical asymptote has shifted 2 units right as well, meaning that there is now an asymptote at x equals 2. This means that our domain must change as well, because the x values can no longer approach 0. Now they approach but never reach 2. So we can write parentheses and a 2. And the graph still continues on to positive infinity, so we can write the other half of the domain to be positive infinity and a parentheses. Therefore, our domain for the function of g of x is 2, infinity.
What about the range of the function of g of x?
As we can see on the graph of g of x, the y values still go from negative infinity to positive infinity. Even after the transformation, our range still remains the same. This gives us our final graph of g of x and our final answer of 2 to infinity for domain and negative infinity to positive infinity for range.
Let me see if I understand this. So first we identified that g of x equals log base 2 of x minus 2 is a transformation of the graph of f of x equals log base 2 of x. Then we found 2 points, plotted the graph of f of x, and used the graph to help us determine the domain and range of the function of f of x. Next, we made the appropriate transformation to give us the graph of g of x, and noted how this transformation also affected the vertical asymptote. We then adjusted the domain to account for this. Last, we used the graph of g of x to help identify the range of the function of g of x.
Sounds like you understand this topic.